Now this cloth simulation for the tentacles is looking pretty cool, but as I've pointed out, this isn't doing any volume preservation within these tentacles. It's not really looking like a solid mass that's wiggling around. And in order to get some volume preservation in here, we're going to need to simulate these as soft bodies. So let's stop that and go back into our setup here. And I'm just going to drag the cloth version of our setup to the side. And we can create a soft body sim by hitting tab and typing Vellum configure and selecting Vellum configure strut soft body. And this is going to create two Vellum constraint SOPs. And the first one is just going to be a cloth constraint type, which is basically the same thing as we already looked at, because the way that these soft body sims will work is by simulating the surface as cloth, but with additional constraints inside the object to help enforce that volume preservation. So let's connect our existing geometry with the pin group into our new Vellum constraints here. And similar to before, I'm going to default this to a high mass because I want these tentacles to feel pretty heavy. And if we display the first Vellum constraint SOP here, this is just creating a normal cloth object like we've already seen. We've got some constraints in here to enforce the cloth behavior of that mesh. And now the second Vellum constraint SOP, this Vellum struts here, is going to create additional constraints inside this geometry. So essentially for all of these points on the object, it's going to search in the direction opposite the normal to find a corresponding point on the other side, and it's going to use that to build these constraints inside this solid object. And if we select our Vellum struts constraints here, you'll see that a lot of these parameters are going to match what we see on the cloth constraints. So we have controls over the stretch, stiffness, and compression, and the damping ratio. We have rest length scale if you want to force some expansion or contraction of these constraints. And some of this stuff will look familiar to what we already saw on the cloth, but there's a different section here for strut search. And this is going to define how these extra constraints are created. So right now, this maximum strut length of 100 means that any point here, when searching opposite the normal direction, can search up to 100 units the opposite direction to find another point to create a strut constraint too. And sometimes if you have large objects, perhaps you don't want really large strut constraints being created. Maybe you only want to enforce some solidity in some of these more defined smaller areas like these tentacles. It's not really an issue here because we don't really have large solid sections of our mesh here, but you can see that some of these points look like they're creating constraints that are fairly far away from the source point. You can see some constraint lines that are sticking outside the mesh and finding a point that's further away than we really need. So if you take a look at these stray constraint lines outside the tentacles there, those will get cleaned up if we start to turn down our max strut length. And you can see as we turn this down, some of those extra constraints are going away and getting cleaned up. And if we turn this down to 6, that gets rid of most of those extra constraints that are sticking outside the geometry. And it's really not a problem for these constraint lines to stick out of the geometry, but because we're really only interested in enforcing some volume preservation, we don't really necessarily want these big long constraints with points that are being constrained to other points that are fairly far away. So this value of 6 looks like it gives us really good coverage within these tentacles, and it cleaned up a lot of those constraints we don't want. You have to be careful because if you make this strut length too small, then you're going to start getting rid of a lot of the constraints that you actually need to enforce this solidity. So in our case, I think a value of 6 is pretty good. And we don't really need to change the other parameters on the strut search here. We can feed all of these points a different vector direction to look in. By default, this is going to use the normal of the mesh, but we have a direction attribute if we want some more customized control over the strut search direction. We can invert the normals to determine which way these points are going to search for other points to connect to. So when we hit invert here, you can see that these points are searching outside of the mesh instead of inside, and perhaps there are some use cases for that, but if you have some decent geometry with well-formed normals, at least for more conventional soft body cases, you probably won't need to do that. Let's turn that back off and look back inside. We can also add some more randomization by jittering the direction a bit, which will affect how those struts are created. We can also increase the number of constraints being generated per point, which is going to give us a much more dense network of struts. Once again, we don't really need to do that. I'm going to leave that at 1 constraint per point. I'll leave the jitter at its default. We can also have some constraints being randomly removed by increasing the detach point chance here. So that could thin out your constraints a bit. Once again, we don't really need that in this case. I'll leave that alone. The seed is just going to randomize our results a bit and give us slightly different variations. And the ray offset is needed so that when a point starts searching for another point, it needs to start offset from the surface it's searching from, so it doesn't immediately hit itself. And that's what this ray offset here does. Once again, we don't really need to mess with that because we're getting some nice struts just by setting the max strut length to what makes sense for our object here. And we can go ahead and start simulating this version of the tentacles. So I'm going to use the same noisy wind setup that we used for the cloth sim. So I'm just going to copy this vellum solver that we already created for the cloth, paste that over here, and let's connect the first and second outputs from the vellum struts to this vellum solver. I'll call this one soft body. And this already has the pop wind setup inside so that we get some nice interesting turbulent wind blowing through these tentacles. And let's do a flipbook to see what this looks like. Now I've only simulated a few frames here because this isn't working properly just yet. We are getting some soft body behavior, but our pin group isn't currently working because we haven't set that yet on our vellum cloth for the soft bodies here. So let's go back to that vellum cloth constraints, and then on the pin to animation section for pinpoints, we'll select that pin group that we've already set up. And now let's run this flipbook once again. Now this soft body simulation is looking pretty interesting. It's not flowing quite as much as I would like. There are a few things we can change to perhaps allow this cloth surface to flex a little bit more. And it does look like in some areas we are getting volume preservation, but things are getting squished maybe a little bit more than I'd like. And you can spend a lot of time playing around with this to get just the right behavior out of this surface. So I'm just going to try a couple things. I'm going to first go to the cloth and turn the stiffness way down. When doing a soft body sim, we can generally get away with a bit less stiffness in the cloth surface because we have these shapes also being enforced by the strut constraints. Whereas if we're only doing cloth, we need to use some higher stiffness values to prevent the cloth from getting completely stretched out. But in this particular case, the cloth constraints and the struts are working together. So I'm going to try just less stiffness at the cloth constraints here. And maybe I'll try raising the stiffness a bit on the struts just to help enforce that volume preservation just a bit more. And now let's resimulate. And now checking our updated sim, this is looking pretty cool. It looks like convincing solid tentacles flowing in the wind here, and I'm pretty happy with this. And there are some parts on this mesh that look a little bit rough, and it's very common with Vellum deformable simulations that you will need to do some additional post-processing to smooth things out or art direct some shapes and finesse things in that way. But this is looking pretty cool, so let's go ahead and cache this out before running those extra post-sim tweaks. So if we go back to our simulation setup and middle mouse on the Vellum solver here, you can see that we have 24 point attributes, a couple prims, a whole bunch of detail attributes and groups, and all of this data is going to take up a lot of unnecessary disk space when we cache this out. So it's very helpful to throw away all of the attributes that you don't need. And there is one attribute that we do need that we don't currently have on our mesh, and that's going to be the rest position. And this will be pretty important for later when doing point deformations. You can potentially refer back to the original mesh before a simulation to get the rest position, but it's often good practice to also store the rest as an attribute. So before we run this sim, I'm just going to add in a rest position SOP. Let's drop this in before our cloth here. I suppose we can wire that in for both the soft body simulation and the cloth sim that's just for reference that we're not actually using. So that rest position SOP will just store the current point positions before the sim in this rest attribute. And then we're resetting our simulation and going in a few frames to do our attribute cleanup. And as we've looked at before, we're going to use an attribute rename SOP to do the cleanup here because this has these useful controls for the delete attributes and keep attributes parameters. And for the point attributes here, we can hit the drop down next to keep attributes, and I'm going to keep the velocity. And in this particular case, the velocity won't be correct once we apply this to the animated creatures flying through space, but generally speaking, velocity is a good attribute to keep, even though we won't use it directly. In this case, we will either use deformation blur or recalculate these velocities with the correct animation, but in most cases you will be keeping that velocity attribute. Most of these other attributes we don't need. A lot of these are related to our Vellum sim setup. So scrolling through all of these, the only one I'm seeing that we do need is the rest position. We don't have any vertex attributes currently. Perhaps we should have set some explicit normals on the surface, but I'm just going to leave this as it is for now unless we find that not having those normals in the attribute is a problem, but I think it'll probably be okay. For the prim attributes, we don't need any of those. So under point, let's get rid of the asterisk, so keep attributes is only V and rest. Primitive, let's get rid of the asterisk, so we're getting rid of all the primitive attributes entirely. We don't need any of these detail attributes either. So on the detail tab, let's get rid of the asterisk there as well. And we also don't need any of these groups either. So let's drop in a group delete SOP and put a star for group names, so that just gets rid of all the groups. So now we only have position, rest position, and velocity, and this will be a much lighter cache than if we stored all of the data that's coming out of the sim. So now we can go ahead and cache this soft body sim to disk. So I'll drop in a file cache, connect that to our cleaned up sim results. I'll point this to geo, creature, and I'll make a new directory for tentacles, soft body, version 1. And the file name will be tentacles softbody.f4.bgeo.sc, and then turn on load from disk. And for the start and end frame, I'm actually going to cache a much larger frame range than our actual shot. So we have a few different creatures flying around in this scene, and I'm going to use the same simulation for the tentacles for all of the different creatures, but we want the creatures to have different tentacle shapes at different times, so we're just going to use time offsets on the same simulation for each one of the creatures, which means we have to simulate and cache out lots of extra frames of the tentacle sim for us to have room to kind of pick different time offsets that look nice and create variations between the different copies of the creature. So I'll Control-Shift-Click the frame range there to get rid of that parameter expression, and I'll cache this from frame 1 to frame 2000. And because this is a fairly lightweight mesh, even though we're caching 2000 frames, this shouldn't be a terribly heavy cache. So now we can save this to disk, and then we can take a look at cleaning up our sim results with some post-processing next.